Hello and welcome to the first edition of Technology Update for 2010. Games are a big part of our lives, something we do for fun from childhood. But it's also a big business and a field for ever-developing technology.
Through the mid-20th century, kids played with pretty basic mechanical toys, but the rise of the computer would start broadening their horizon. The first game interfaces in the 70s featured very primitive controls and graphics. By the early 90s, the games were a bit more colorful, but still 16-bit at best. The last decade has seen the explosion of increasingly lifelike gaming with 3D graphics. The control interface has also evolved to imitate real motion more closely.
Traditionally, we thought about interfacing with our hands, our feet, or even our whole bodies. But leading scientists and inventors are looking at a more cerebral approach that might give us better control.
A special brain research group at Moscow State University's biology department thinks the future will largely depend on what's between our ears. Their research is helping map the brain's response to a wide range of actions and stimuli, and Professor Alexander Kaplan hopes to harness its power for tangible benefits. Much of the interest in this technology has come from medical circles, where patients with paralysis or other conditions might regain motion without any necessary physical input, using only the power of their minds. But they're also investigating ways healthy people could use brain-computer interface technology to improve their lives or even entertain themselves. With laboratories around the world pursuing similar goals, their brain puzzle is one of the most advanced developments in the field.
Now we get a chance to test out Moscow State's program and the powers of my own brain. The first thing we do after putting on the headgear, a little bit of gel on the electrodes, is to pick a picture that the program will scramble into 16 blocks in a puzzle. Then we start the calibration process by clicking this button.
So how do we know what's going on in a human brain? Non-invasive brain-computer interfaces use electroencephalography, or EEG technology, with electrodes placed on the scalp of a test subject, detecting the electric signals put out by different parts of the brain. These signals are then amplified and digitized so they can be read by computer programs. Specifically designed software uses transition algorithms to sort out what the variations in signals from different brain areas mean and then display the results. Moscow State's puzzle game takes information from the rear part of the brain, the most active area in determining a person's visual processes. In the calibration phase, the player should focus on the block in the scramble picture that flashes, staying focused on the same block while the rows and columns light up in random sequence. The technicians recommend that you concentrate by trying to count the number of times the block you're staring at lights up. The system is memorizing the electrical activity measured when you're looking at a particular block, so it will know where you're looking later.
To start the game itself, you get to pick any 3 blocks simply by just focusing on them for a brief period of time.
As in the calibration, you focus on one block throughout the entire series of flashes. Only this time, you get to choose which one.
If the block you were focusing on is the one that appears on the right, then the calibration between your brain and the system is working properly. If not, don't be afraid, it doesn't always work the first time. Just hit next and go on.
In the main part of the game, 2 blank spots in the unfinished puzzle light up in white. You pick a block on the left that could go in either place and focus on it.
In this case, I didn't get one of the 2 right. More likely than not, my focus was a little bit off. There we go, finally got one right. Focus really is the most important thing. I find if I'm not absolutely relaxed, sitting as quietly and carefully as I can, it flashes and I don't end up filling in the blank on the right where it's supposed to go. Sweet, so you can see I'm really starting to pick up some of the pieces. Once you get your mind focused, the connection really works quite well. I probably jinxed it. You can see, I think my eyes got a little tired there and I missed one. Let's try it again.
A brain-controlled car? No problem. Just think about where you want it to go. While Moscow State University's developers are doing top-notch software, the Russian company Neurobotics is pioneering the latest hardware. They're evolving EEG equipment to provide higher degrees of precision so ever more complicated activity can be controlled with our minds. Professor Kaplan consults with Neurobotics regularly to share scientific expertise and see how the latest brain-based gadgetry is developing. Their projects are often parallel, but as a private company, Neurobotics has more flexibility with funding. Letter recognition could be the key to a whole range of empowering or time-saving devices. It's just a matter of unlocking the processes in our head that control the action. That means endless hours of writing code, testing ideas on human subjects, and staring at EEG output. New models of the helmets are always in the works. More electrodes means more data collected, and more data means more options. That's just one link in the chain, as the amplifier has to evolve alongside. It takes a lot of people to put all the pieces together, but they're making big steps in unleashing the power of our minds.
Back in business, it seems to me that it really does know what I'm thinking. You would probably have difficulty believing that something like this could really read your mind that clearly. But without touching anything, I'm literally making things move from the left over to the right, exactly where I want them to go. Alright, down to the last one. This one should be easy. It's the last piece still showing on the left side here. All I have to do is move it like I've moved the other 15 pieces over to the right, and we're done. Oh, man. Somehow me and this last piece aren't seeming to get along. I don't know why it understood me so well until now. Probably because I thought in my mind that I already had it in the bag. Got it. So there you have it. I'm probably better at directing a game with my brain than I am with my own two hands.
One of the first attempts to use brain-computer interface technology for a marketable form of entertainment is Mindball. According to its designers, the electrode headbands measure the player's brain activity through the forehead. Moscow State's Professor Kaplan is intrigued by the game, though it differs from his puzzle.
This is another type of brain-computer interface where we need to focus on our condition. The more I relax, the better the chances that my ball will move towards you.
So what does this mean? The ball's sitting more or less in the middle. Why?
It means that you and I are equally relaxed. You see on this diagram that the height is more or less equal here and there. We're now in a period when many research laboratories are working to make concrete steps to real games. We're only in the first stage. A person plays, it's entertaining for him, but in the meantime, he is developing his concentration skills.